This is 2019, an Alum Odyssey Part 3. So my crystals have not grown a lot since the last video. There are still 6 crystals in the container and they are larger than they were in the last video. Here they are. Here's a picture of them. And they vary in size and none of them are the exact same shape and some of them are more clear than others. The differences in clarity of the crystals are likely due to varying amounts of impurities that remain despite our attempts to clean the product during the original experiment. There is less solution in the container now, as you can see here, which makes sense because the crystals are growing larger as the solution evaporates. There's been a higher average temperature in Evanston since the last time we took a video, so there's a possibility that the solution evaporated at a slightly faster rate than it was before the second video. Crystals grow faster in warmer temperatures because solvent holding the crystals evaporates more rapidly. This would theoretically make the crystals be a little less high quality. The added crystals that were formed during this time would be a little less high quality because the ions would have had a little less time to make the perfect lattice. If I wanted to grow a single large crystal from a saturated solution of alum, I could put a small amount of excess alum into the solution once it was already saturated. I would do this because the alum that's dissolved in solution would form a lattice around the extra alum that we would have placed there, and it would form, and the additional alum crystals would form around the existing alum instead of in various crystals. This somewhat relates to equilibrium because adding more reactants would shift the equilibrium towards the right, creating more of the crystal alum product. So adding reactants in the form of, in the dissolution equation as a solid would end up creating the neater crystal. Because we lack this, however, we lack the extra alum added. The alum crystals formed in various places around the edges of the container. However, if we were trying to grow a high-quality single crystal, we could still use the Kimi wipe on top of the container in order to minimize evaporation of the vessel and form the high-quality crystal. And despacing is the consistent distance between neighboring parallel planes of a crystal. It's related to the periodicity in a crystal, and which is the small atomic scale pattern that repeats itself continuously in every direction. Despacing is important because the distance between atoms and planes in a crystal gives meaning to X-ray diffraction, which uses wave interference, different patterns of X-ray waves, to characterize the gap that the waves are moving through. Despacing can be telling of the properties of a crystal. It's useful in predicting how a crystal would interact with other molecules. An example, if it's possible for smaller atoms to move between the spaces and form bonds with the atoms of the crystal. And you can also find the crystal structure of an unknown material, which can be telling of the atoms in it if you know the X-ray data. Knowing the despacing can also be useful to determine unit cell dimensions or measure the purity of a sample. And so we calculated the spacing for the data in this example, and I did this by using Bragg's law, and then Bragg's law is just n times lambda equals 2d sine of theta. And so the sine of theta I got from the original X-ray data that was online, which can be seen here. And I used the peak, which was at about 20.7, I estimated. And I found the lambda value from the top of the screen up here. And so with those values, I had lambda equals 0.15418, 2 theta equals 20.7, so I had to divide the theta by 2, as you can see here, in order to get 10.35. And then the n equals 1 was given to us. And so I just plugged those things into the equation for Bragg's law. And I found, after doing this and simplifying to find the actual despacing, I found that the despacing is 0.4291 nanometers. And then the 2 theta position with the highest peak has the highest intensity of light hitting it, and is therefore the middle of the 2 gaps. So it's in the exact middle of 2 gaps.